On July 10th, China caught a falling rocket with a giant net at sea. The Long March 10B had already placed a satellite into orbit when its first stage descended toward an offshore platform, instead of landing on legs like a Falcon 9. Hooks on the booster engaged moving cables and left the stage suspended above the deck. The method may offer a major advantage. By shifting part of the landing system from the rocket to the platform, China could reduce booster weight and preserve more capacity for payload. But recovery is not reuse. Engineers must now inspect the engines, find hidden damage, refurbish the stage, and fly it again. Until China can repeat that process quickly and reliably, this remains an impressive catch, not a launch system capable of closing the gap with SpaceX. The catch began like a conventional launch. At 12:15 in the afternoon, the Long March 10B lifted off from Hainan, carrying an undisclosed satellite. The vehicle stood about 63 meters tall, measured 5 meters across, and weighed roughly 760 tons at launch. A few minutes later, the rocket split into two different machines. The upper stage continued toward orbit with the payload. The first stage, which contains the main engines and much of the vehicle's cost, turned back toward Earth. That distinction matters. China did not recover the entire rocket. It recovered the most valuable section, the part normally discarded after only a few minutes of work. The booster then passed through a controlled return. It adjusted its attitude, slowed with its engines, used aerodynamic surfaces to guide itself through the atmosphere, and aimed for a recovery platform waiting offshore. The platform was enormous. It measured roughly 144 meters long, 50 meters wide, and displaced about 25,000 tons. Yet the booster still had to enter a narrow capture zone with enough precision for 4 hooks near its upper section to engage the moving cables. When they did, the stage stopped above the deck and remained hanging inside the structure. China had proved that it could return an orbital-class booster to a chosen point at sea. But the most unusual part was not the return itself. It was a decision to build the landing system into the ship instead of the rocket. That decision only matters if the booster can do more than survive the trip home. In spaceflight, recovery and reuse are not the same achievement. Recovery means bringing the stage back without destroying it. Reuse means proving that the same hardware can be inspected, serviced, and launched again without rebuilding most of it in the process. SpaceX learned that difference the hard way. Falcon 9 first landed an orbital-class booster in December 2015, but the first successful reflight did not happen until March 2017. Between those two milestones came months of inspections, engine testing, structural analysis, and work to understand how much damage a booster accumulates during launch and return. Even that first reflight did not create routine reuse overnight. SpaceX needed years of additional missions before recovered boosters became normal operating equipment rather than carefully managed experiments. By 2026, some Falcon 9 first stages have flown dozens of times. That is the standard China is now being measured against. The Long March 10B has completed the first step. It returned from an orbital mission and was recovered intact enough for engineers to examine it. But no public evidence yet shows how much refurbishment it will need, how long that work will take, or whether the same stage can repeat the mission safely. A reusable rocket is not defined by the catch. It is defined by the turnaround after the catch. And if China hopes to make that turnaround competitive, reducing the amount of hardware carried by the booster could become one of the design's most important advantages. Landing legs sound simple, but on a rocket they're expensive, and the one currency engineers can never ignore: mass. A Falcon 9 carries 4 deployable legs from liftoff to landing. Those legs need hinges, actuators, locking systems, and reinforced attachment points strong enough to support the booster after touchdown. The Long March 10B takes a different approach. Instead of carrying a complete landing system, the booster carries 4 relatively light hooks near its upper section. The heavier machinery stays at sea, built into the recovery platform. According to China's launch authorities, that arrangement could reduce the mass carried by the rocket and preserve more of its performance for payload. The exact saving has not been published, so it is too early to know how large the advantage really is. But the engineering logic is clear. If the booster carries less recovery hardware, more of its energy can be used to place cargo into orbit. That does not make the landing system disappear. It moves it. The platform now needs a massive steel structure, moving cables, sensors, power systems, and equipment capable of absorbing the energy of a descending first stage. It also has to hold position at sea while wind, waves, and current move the vessel beneath the rocket. So China has made a deliberate trade. The flying vehicle may become lighter and mechanically simpler, while the recovery operation becomes larger, more specialized, and more dependent on offshore infrastructure. A Falcon 9 brings its landing system with it. The Long March 10 must meet a machine waiting at sea. And for that trade to work, the booster and the platform cannot simply arrive in the same area. They must find each other, align in motion, and complete the final capture within seconds. The final approach is less like a landing and more like a controlled rendezvous between two moving machines. After separation, the booster continues briefly on its existing path before turning so its engines face forward. It then performs a series of burns to reduce speed, reshape its trajectory, and guide itself back toward a recovery zone. Grid fins help steer through the atmosphere, making small corrections as air begins to act on the vehicle again. But reaching the ship is only the first half of the problem. The platform itself is moving. Even with dynamic positioning, a vessel at sea still rises, falls, pitches and rolls as waves pass beneath it. Wind and current can push it offline. At the same time, the booster is descending vertically, correcting its position while burning fuel and fighting the same weather. That means the recovery system cannot behave like a fixed target. LiDAR sensors mounted around the capture structure measure the booster's distance, direction, and angle as it approaches. The system then adjusts the steel cables inside the net, moving the capture area toward the hooks on the rocket. Those hooks sit near the upper section of the booster. As the stage enters the structure, the goal is not for all four to strike one exact point. The moving cables create a larger effective target and can compensate for some error in the final descent. Once the hooks engage, the cables do not stop the booster instantly. That would create enormous loads and could tear the attachment points from the structure. Instead, the system allows the cables to move under controlled resistance, absorbing the booster's remaining energy over a longer distance. The principle is similar to the arresting gear used on an aircraft carrier. A landing jet catches a cable, and that cable pays out while machinery below the deck slows the aircraft. China's platform applies a related idea vertically. The rocket descends into the net. Its hooks catch the cables, and the braking system brings the stage to a controlled stop. The difference is that an aircraft carrier operates on a deck designed around one direction of travel. This system has to manage motion in 3 dimensions. The rocket can drift, tilt, and rotate. The ship can heave, pitch, and roll. The capture only works if propulsion, navigation, ship positioning, LiDAR tracking, cable movement, and hook engagement all happen in the correct order. And the net is not passive. It is actively helping the platform meet the rocket during the final seconds. That makes a successful catch a genuine engineering achievement. But it also concentrates the recovery loads into 4 small attachment areas on a booster that is meant to fly again. What engineers find around those hooks, inside the tanks, and through the engine structure will determine whether the system merely caught the stage or preserved it. Preserving the stage is where recovery becomes a materials problem, an engine problem, and eventually an economic one. The booster has already endured liftoff vibration, maximum aerodynamic stress, engine shutdown, atmospheric reentry, restart, and the final capture. Each phase loads the vehicle differently. Metal expands and contracts. Tanks are pressurized and emptied. Valve cycle. Turbo pumps spin at extreme speed. The structure bends, heats, cools, and then absorbs a final set of forces through 4 hooks that have never been used this way on an orbital booster before. Some damage is obvious. A cracked panel, a distorted hook, or a leaking seal can be found quickly. The more dangerous problems may be microscopic. Fatigue around an attachment point, heat damage inside an engine, or a small deformation that only becomes critical on the next flight. That is why engineers cannot simply refuel the stage and launch it again. They need to inspect the engines, pressure test the tanks, examine welds and load-bearing structures, verify the avionics, and determine whether any component has moved outside its design limits. The sea adds another complication. The booster was recovered offshore, where salt and humidity can contaminate electrical systems, mechanisms, and expose surfaces. Even if the stage never touched the water, the recovery process still has to protect flight hardware while it is secured, transported, and returned to land. China says this booster is expected to fly again before the end of 2026. That ref flight will be far more revealing than the catch itself. If engineers replace major components, dismantle the engines, or spend months repairing the structure, the stage may be technically reusable but operationally expensive. A rocket only creates a real advantage when the cost and time required after recovery are lower than building a new first stage. SpaceX faced the same transition. Its first Falcon 9 landing came in 2015, but the first ref flight followed more than a year later. Routine reuse took many more missions, because every flight produced data about which parts survived, which parts wore out, and which inspections were truly necessary. China now has to build that knowledge from its own recovered hardware, and it needs to do more than prove the idea once. China is building launch capacity for satellite constellations, commercial missions, and a wider space program that will demand far more rockets than a single successful demonstration. That demand is growing fastest in low Earth orbit. The Long March 10B was not built only as a technology demonstrator. China's launch authorities describe it as a commercial vehicle for large satellites, communications missions, and the deployment of orbital constellations. In its reusable configuration, it is designed to carry about 16 tons to low Earth orbit. That matters because constellations change the economics of launch. A single scientific satellite may require one mission. A constellation requires repeated launches of similar payloads, often over many years. If every mission consumes an entirely new first stage, production has to grow almost in step with launch rate. Reuse offers another path. Instead of building a complete booster for every flight, an operator can maintain a smaller fleet and fly each stage repeatedly. That can reduce the pressure on factories, engines, materials, and assembly lines while increasing the number of missions the same industrial base can support. But only if refurbishment does not become the new bottleneck. If a recovered stage needs extensive repairs or months of inspection after every mission, the advantage disappears. The rocket may return, yet still fail to increase launch capacity in any meaningful way. The stakes also extend beyond commercial satellites. The Long March 10B belongs to a wider rocket family connected to China's next generation of crewed and lunar launch systems. Flight data from its engines, structures, guidance systems, and recovery hardware can feed into those larger programs. So the value of this catch is not simply that China may save money on one booster. It is that successful reuse could allow the country to place more payloads into orbit without expanding rocket production at the same rate. That is the capability China is pursuing. But one recovered booster does not yet create it, and that is where the comparison with SpaceX becomes much less flattering. SpaceX is no longer proving that booster reuse can work. It is operating an entire launch business around it. By 2026, Falcon boosters had completed more than 600 landings, while individual first stages had flown dozens of missions. That experience produces something China cannot gain from a single recovery: data on how engines age, where structures fatigue, which components require replacement, and how quickly a booster can safely return to service. The comparison is not simply landing legs versus a net. China's design may reduce the hardware carried by the rocket and create a larger capture area during descent, but it also depends on a specialized offshore platform, complex cable machinery, precise ship positioning, and weather conditions suitable for recovery. SpaceX carries more landing equipment on the booster, but the surrounding system is mature. Its ships, inspection procedures, spare parts, refurbishment teams, and launch infrastructure already support a high flight rate. China has demonstrated a credible alternative. What remains unknown is how long refurbishment will take, how much recovery will cost, how often weather will interfere, and how many flights the engines, hooks, and structure can survive. The next decisive test is expected before the end of 2026, when China plans to fly the recovered stage again. One successful ref flight would not erase SpaceX's lead, but it would prove that the net preserved usable flight hardware, not merely a booster that survived the fall. China has shown that it can catch a rocket. The real breakthrough will come when the same rocket rises from the launch pad again,